All right, let's look at some other reactions uh, that go through this radical mechanism. And let's return to look at the stability of our radicals and note that yes, the primary radical is less stable. Note methyl radical is even less stable, just like a methyl carbocation would be. Secondary radical is more stable than primary. Tertiary radical is more stable than secondary. But the allylic radical, a unpaired electron on a carbon next to the carbon of a double bond, the allylic radical is the most stable. Recall with carbocations, allylic carbocations are about the same stability as secondary carbocations. With radicals, allylic radicals are more stable than tertiary radicals. The problem is it's not the easiest to make these tertiary or these allylic radicals selectively using just our normal methods, because you tend to get a mess. Anyhow, the reason these allylic radicals are more stable is because we have this resonance. Note that if you had this allylic radical here, we could take this double bond and move it over here, and an unpaired electron over here as a resonance form with this allylic radical. So resonance makes you know that the actual beast in solution, the resonance hybrid, is more stable than you think it would be. All right, so the question is then, how can we selectively generate this radical versus others that we're going to be talking about? Because we're going to find there's other ways we can deal with double bonds. We can do radical addition to double bonds, as we mentioned before. How do we make sure we make an allylic radical versus doing radical addition to the double bond? The way it works is a good old buddy NBS, N-bromosuccinimide. And you will recall that N-bromosuccinimide is a molecule that keeps a low concentration of bromine around. Now, if you're interested, I'm not going to hold you to this, but here's the mechanism down here of N-bromosuccinimide with light and how we will generate low concentrations of Br2, which will then do our radical mechanism and selectively put the bromine in the allylic position. What you need to know, what you need to keep in your head is, if you see an alkene and NBS with light or peroxides, ROOR is peroxides, light or peroxides, this is radical conditions. NBS, radical conditions, is going to put a bromine in the allylic position here or here, but that's the same molecule, so just put the bromine here. Recall, if we had an alkene and we just added bromine to it, Br2, normally it's going to react very quickly. This is a bromine test to put two bromines on there. All right, so that's the big deal there. So that looks pretty good. You see NBS, light or peroxides, or any sort of radical conditions, you know we're going to selectively put the bromine in the allylic position. Recall last time we talked about NBS, it was used for making halohydrins, and NBS with water, if you had a double bond, you have NBS and water, that would put a bromine on one carbon and an OH on the other carbon, but that's not radical conditions. Here we have radical conditions, selectively brominating the allylic spot. The problem comes with the whole resonance forms here. Note, look at this. We've got CH2 double bond CH, CH2, CH3. NBS radical conditions, we know, okay, allylic radical, we're going to put the bromine at the allylic position on the carbon next to the carbon of the double bond. We'd expect the bromine to go here. And what we find is, yes, we get the bromine on that spot, but we also get the bromine at the end and the double bond in between the two carbons in the middle here. So if we're looking at this molecule, yes, we'll put a bromine here, but we'll also put a bromine at the end, and the double bond will be here in between these two carbons. What gives? The resonance. Recall, this is going to go through the allylic radical intermediate. We're going to start with hydrogen abstraction, which makes this allylic radical, but allylic radicals have resonance forms where we move the double bond over and the unpaired electron over here, so we get this allylic radical also. Both of these will exist in solution, therefore the bromine will add here to this allylic position from this resonance form. It will also add here to this allylic position of this resonance form. So keep that in mind because you're guaranteed to see it on an exam. All right. Moving on, let's look more at double bonds. If we don't selectively brominate allylically, we can just do radical addition to double bonds, and the reaction that does that is HBr and radical conditions, light, peroxides, heat, that type of thing. Recall previously, if you just had a carbon-carbon double bond and you added HBr to it, that's Markovnikov, right? Remember, the double bond would attack this hydrogen. Remember, Markovnikov's rule says the hydrogen would go on the carbon with more hydrogens to make the more stable secondary carbocation, so the bromine would react here. This is what you'd expect, CH3, CHBr, CH3. That's old news. Note, though, if you have the same starting molecule and you add HBr but you put it under radical conditions, we put the bromine at the end, CH3, CH2, CH2Br. Normal conditions, the hydrogen goes on the carbon with more carbons. Or excuse me, normal conditions, the hydrogen goes on the carbon with more hydrogens. Radical conditions, the hydrogen goes on the carbon with less hydrogens. Anti-Markovnikov. So yeah, this is pretty nice. We start the same starting material. You can decide, well, where do you want the bromine? You want the bromine to go on the middle carbon? You want the bromine to go on the end carbon? You want it to go on the end? Okay, add the HBr under radical conditions, anti-Markovnikov. You want the bromine on the middle carbon? Okay, that's just normal addition of HBr, follows Markovnikov's rule. Recall, as I had mentioned, in the mechanism for the normal reaction, the double bond attacks the hydrogen, and the hydrogen goes on the carbon with more hydrogens. The hydrogen gets added first, and it goes on the least substituted carbon to generate the more substituted carbocation. When looking at the mechanism of radical addition, the first thing, you have your peroxides here, add a little heat or light to generate these two peroxy radicals. These peroxy radicals then will react with the HBr to do some hydrogen abstraction to make some alcohol and this bromine radical. And note, it is this bromine radical that is the radical of the propagation step. So this reaction really has two initiation steps. The first step is to make the alkoxyl radical, and the second step is to make the bromine radical from HBr. This bromine radical will then react with the double bond. So when we're adding HBr during radical mechanisms, we're adding bromine first. Recall, under our normal mechanism, we added the hydrogen first. Here we're going to add the bromine first. We still want to generate the more stable secondary radical, so the bromine will go to the carbon with the more hydrogens on it. The bromine will go to the less substituted carbon to generate the more stable secondary radical. And then the secondary radical will do hydrogen abstraction and generate another bromine radical. Bromine radical plus the double bond puts a bromine on the terminal carbon here. Reacts with HBr, generates more radical. There's our propagation steps. And eventually, after we've run out of reactants, a bromine might find another bromine, make Br2. There's a couple of different termination steps possible. All right. And interesting enough, HCl and HI and HF do not add to alkenes via radical addition. This is only with bromination. That's the only way it'll work. Okay. Now we come to the last letter of the semester, polymers. Polymers are large molecules that are made up of small repeating molecules we call monomers. And we're going to start looking at synthetic polymers. We tend to call them plastics. Polyethylene, polyvinyl chloride, polystyrene, these are all sorts of plastic type of things. All right. And what happens is, if you have, say, ethene, and a whole bunch of ethene, just a bunch of ethene molecules all together, you can actually hook this ethene onto this one with a bond, and then hook it onto this one with a bond, and this one on the bond. So this whole chain of CH2s is our polymer. And since it started with, well, the IUPAC name is ethene, the common name is ethylene. So we call this chain of ethylenes polyethylene. So each CH2 is the monomer. Note, when you see this, it's just CH2, 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 CH2. The monomer is not just CH2. The monomer is CH2, CH2. It came from these two carbons. Note, your monomer always has to have two carbons in it that were originally double bonded together. So this is your monomer in just ethylene, and this is your polymer. All right, here's another one. This is called vinyl chloride. And so if you link these together, you make polyvinyl chloride. And due to the way that radicals work, you will always find the radical intermediate will have the radical on this carbon here, because it's with its chlorine on here, it's the more substituted carbon. So you will always make the chain, this chain will always be made like this, where you'll have CH single bond, CHCl single bond, CH, CHCl single bond, CH, CHCl, excuse me, single bond CH2s here. But it'll always look like that, because as the polymer is propagating, as you're adding more and more monomers on there, we'll always go through the more stable polymer and the more stable radical. The more stable radical is a secondary radical. Heavens. All right. So, note, here is another monomer. It is the molecule styrene, a benzene ring with a vinyl group on there. And if you put it under radical conditions, you'll make polystyrene. And this polystyrene is nice. Those phenyl rings like to kind of stack onto each other and form like a film. So as you're making the styrene, you're blowing air through it. All that air gets captured in big bubbles or little bubbles in your styrene, and you make styrofoam, polystyrene, which is mainly air trapped in these sheets of styrene molecules that are bonded together, make polystyrene. And if you have propene, note, you always have to have the CH2 double bond carbon. This carbon here will be bonded to this carbon of the next monomer. So this CH3 is always going to be dangling out here. It's always going to be this CH2 bonded to this CH, bonded to the next CH2, bonded to the next CH, bonded to the next CH2, bonded to the next CH. And the methyl's hanging out, so that's polypropylene. Note, then someone took CF2, double bond CF2, Teflon, tetrafluoroethylene, so this is polytetrafluoroethylene, and that's Teflon. Because fluorines really hold their electrons, and if they're holding electrons really tightly, then that means that you don't get a whole lot of interactions. No, it's not polarizable. Fluorine is not very polarizable. Therefore, you don't get very many dipole-dipole intermolecular forces, which means things do not stick to Teflon. Something to note, that when you think of Teflon in general, you think of nonstick cooking pans, which is true. But in science, if you ever used a burette and you know you had that white material on that stopcock, that is also Teflon. Teflon is used quite a bit in science whenever you have two solid pieces that might be rubbing together. A little Teflon coating means they're going to slip past each other much more nicely. All right. And while we have discussed it, here is the mechanism of the polymerization reaction. I'm not going to hold you accountable to the mechanism, but it is very same. It's the same as the previous mechanisms we've been looking at. Also note that there are natural polymers. Proteins are just a polymerized amino acid chain. Carbohydrates are just polymerized sugars, glucose and then another glucose and another glucose and another glucose, and you've got starch. All right, cool. Well, that ends the semester. This is the end of chapter 15.